This looks. Could you go back,
No,
please?
yeah. Sorry, bit ahead of myself there.
Yeah. Yeah. This is a bit of a technical topic, rather obscure. I've tried to lighten it up as much as I can. For people who can hang on to the bitter end, they'll find something which, when I talk about it, you'll see it gave a bunch of metallurgists at least, made them very, very happy for about 10 years after this project finished. So we'll commence, shall we? Well, this is not about the combined cycle. People confuse the closed cycle with the combined cycle for power generation, but I was persuaded to say something about the combined cycle gas turbine for power generation because it is very, very important. When the wind isn't blowing, it'll provide up to about 60% of the energy, the electrical energy needed in the country. And it's a very flexible system. This week, they virtually shut all the combined cycle plants off because there was a lot of wind blowing. So I'll say a little bit about that. And then I'll start moving on to the real topic of the real subject, which is the closed cycle. But I have to explain how a gas turbine works because I'm fed up with people saying it's bang, squeeze, pop, and so forth. It isn't anything like this, anything like this. And you need to understand how the gas turbine works. Otherwise, you won't understand how the closed cycle gas turbine works. There's some prehistory about the industrial gas turbine, and I'm glad that there's one gentleman who came along tonight specifically to hear about that. Then we'll have to move on to the thermodynamics of the closed cycle gas turbine and where it all really began in Switzerland and moved then principally into Germany, a little bit into France, and a tiny bit into Britain. And then how I got into it, the British Gas Closed Cycle Gas Turbine project, well, how I literally put that together. And has it a future? Well, like hydrogen, maybe. Okay, so let's move on.
Just hidden the slide. Hang on, I've got to try and find how to push it on. It'll be that one. Nope. Sorry. Me trying to be clever. There we go.
Well, here we have the combined cycle gas turbine for electricity generation. And if you notice on the left-hand side, we're not dealing with anything theoretical. We're talking about a really big a plant with a lot of output, 480 megawatts, that if you'd got maybe about 30 of these, you'd have enough power to run the country. And it's very efficient, 63% efficient. Those of you like my age will remember a good steam plant was running at 35% efficient in the 1960s. Well, looking at the picture here, if you can pick out, I'll have to go to the picture. Here is your industrial gas turbine here. And it's producing about 2/3 of the power in the plant. And you've got a shaft drive through to the alternator. Well, industrial gas turbines are quite different to what you have in jet engines. Thermodynamically, they're different. They produce a lot of very hot exhaust gases, and that goes into the HRSG heat recovery steam generator, which is a glorified boiler. Here we are on the right-hand side. of the screen. That's a very unusual boiler by conventional standards. It produces steam at 3 different pressures. A normal steam plant produces steam at 1 pressure. The steam goes right over to the left into the steam turbines. And that too is connected on a shaft through to the alternator. And they all rotate at the same speed. Grid frequency in America, this is an American slide, so it's 3,600 RPM, 60 cycles. You change. Sorry?
Sorry.
Some interference on the screen.
We do.
We do we? Oh, right.
There you go. That better?
Those are the outside people watching, are they?
They are, yeah.
Right. Okay. So I think we can go on to the next slide. Right. Here we are. Well, again, I repeat, modern combined cycle plants are running at 60 to 63% efficiency when they're at full output. A great thing about them is that the construction time is unbelievably short, 2 to 3 years, and it is that which has killed nuclear. You can build these plants and get your money back quickly. You can't do that with certainly with nuclear plant, and you're struggling to do anything like that with steam plant. The capital costs are relatively low by today's standards, 700 to 900 pounds per kilowatt. Another great feature is that you can put them anywhere. They don't require a river to condense the steam. There's so little steam coming through these plants because it's only a fairly minor part of the energy system that you can have air-cooled condensers. Start up to full load very, very quick, 3 to 12 hours. Again, you contrast that with nuclear, which I suppose you'd be talking about a fortnight. And low staff requirements, 10 people per shift. And I think this might be an exaggeration. The drawbacks is that they need natural gas. They can't use coal or heavy oil. So you have to have a cheap gas. When you at part load, the efficiency starts falling away. Once you're below 70% efficiency, 70% output, the efficiency is really dropping away. We're now in a situation where we've got high fuel costs, which is one reason why combined cycle in this country is up and down all the time in terms of output. They're not very good for carbon capture because the carbon dioxide content of the stack gas is low, which is one reason why, although they keep talking about carbon capture from these plants, it's always, in another 5 years, another 10 years. And they're not very good for district heating. Okay. Well, this is, I want to see if you're awake already. What is the name of this plane? Right, good. Okay, right, next. Well, this is the Rolls-Royce's crappy jet engine. The Rolls-Royce 100, which was started its design life under Mr. Griffiths, or Dr. Griffiths, I have to say. But joking aside, it's a good way of showing you how a gas turbine works. You have a compressor which is dragging in cold air from the atmosphere. And that's a very important feature of gas turbines. They like to have cold air coming into the compressor. It increases output and it increases efficiency.
I'm just doing the bottles. I'm just doing the 2 bottles. Is she coming down?
No, she bloody well isn't.
All right.
And it's compressed in the case of the Avon to something like about 8 bar pressure, 8 times atmospheric pressure. And it's squeezed, the air is squeezed into a small volume. It then goes into the combustor, and you're burning fuel in the combustor. And all that the combustor is doing, forget about the flame inside, because the flame is only a small part of the products of combustion from the flame, only a small part of what's going in there. It's heating the air and it's expanding it to say something like about 3 times the volume of the air that was going in. And then it goes through the turbine. And there's a lot of air, of high volume of air going through the turbine. And there's so much going through, there's enough power coming from the turbine to drive the compressor. And in the case of a jet engine, enough energy left over to produce a high velocity airstream to drive the Hawker Hunter along, providing the pilot doesn't fire his guns. Right. Okay, right.
Yeah.
Okay.
I know. I'll move you off. There you go.
Well, one of the first steps that was done with gas turbines was to see whether they could produce, this is what we call the open cycle gas turbine, to see whether we could produce power. As I've said, you know, you've got that high velocity airstream coming out of the turbine. Could we do something other than just use it to push aeroplanes forward? Well, obviously, you can put another turbine at the back end of the plant. And that is another option if you want to generate power. This General Electric aero-derivative gas turbine, as they call it, is comes straight from a military jet engine. The great thing to remember is that you can change in the front part of the engine, it's variable speed, but with the turbine blades at the back end, it's running at 3,600 RPM. Okay. Now, this is some of you might know something about this. This is what the Great Western region bought from Boveri in Switzerland, and they wanted a really powerful locomotive for hauling trains up severe gradients. And it worked. The trouble is that if they used ordinary fuel oil, the ash in the fuel oil eroded and corroded the turbine. And if they didn't get the burners working properly, you got oil going over into what was called the recuperator. That's a part of the arrangement to improve the efficiency, and that used to catch fires. But I put that up partly, well, for another reason. If you look at the top corner of this screen, it says built by Boveri, Switzerland. And this is a handy way of getting onto the next slide. The gas turbine, the industrial gas turbine, started in Switzerland. Don't let anybody tell you any other. It started there, and Boveri, which has now been absorbed and reabsorbed by various companies, worked on gas turbines for a very long period before they had success. Let's go on to the next slide. And this is their first attempt. They took a German idea and they came up with this, the Holsworth gas turbine, which really looks like an abortion. Down by the bottom of the screen, you'll see a number of cylinders, apparently cylinders. Those are producing a kind of an explosion of gas and air, which drive the turbine, which is towards the top of the picture. But the next slide will clear it up a bit more. You've got a two-stage turbine in the center of the screen, and that's being fed by, literally, it is a series of explosions coming from those cylinders arranged around the bottom of the this setup. And that turbine drives the generator. And it was reasonably efficient. If you just got gas to a cheap gas to burn, this was the way to do it. And Brown Boveri built a number of these, and they sold them. You know, not a lot, but they were successful. And it was this that started Brown Boveri on the route to building the first industrial gas turbine. Next. And here it is. You can go and see it as an industrial monument over in Switzerland. And it came out in 1939. And I think this is before anybody was flying a jet aeroplane. But in actual fact, the world generally knew of what Brown Boveri were doing because they were telling people about it. This was not secret. They were telling people, yes, we can build industrial gas turbines, and we can put gas turbines into oil refineries. We can use them to produce a pressurized boiler, and we know all about making turbines, and in particular, making compressors. And I have to say, all of this rubbish that we hear about Griffiths in this country, coming up with the idea of a compressor for a scientifically designed compressor. At the time he was talking about it in principle, Brown Boveri were actually building hardware. Okay. Now over in another place in Switzerland, Escher Whyss AG in Zurich, they got to hear about what Brown Boveri were doing, and they were looking for a way in. And they came up with the closed cycle gas turbine. And the man on the left, accurate, I probably got his name wrong, was a rather theoretical type. And it was he who came up with the idea of calling the speed of sound Mach 1. And he was quite good at turbine design. And his friend, Kurt Keller, was rather more hands-on as far as I can gather. There's a book that has just come out about these two people, that includes these two people, which is well worth reading. They were in close contact with what was going on in Germany. Certainly the Swiss helped Germany with the design of jet engines. And they were so well in touch with what was going on in Germany that they suggested a nuclear-powered closed cycle gas turbine, right? Now, what about the closed cycle gas turbine? The great thing about it is that unlike other kinds of gas turbines, which can only use things like stuff like high grade kerosene or highly pure natural gas, the closed cycle can use any kind of high temperature energy source, coal or source that will produce a hot heat at high temperature, coal, heavy oil, nuclear heat. It's actually, a closed cycle is actually very efficient at low outputs, better than steam engines, and that's why I think it was picked up by some organizations. Maintains the efficiency at reduced output, unlike a normal gas turbine, and the reject temperature is high, so it makes it good for combined heat and power installations. Okay, touch again. The closed cycle operates with a pressurized gas, so you're able to shrink down the compressor and turbine. They're physically small. High rotational speeds come with that, so you often need a gearbox in the system. Because the thermodynamic cycle is more complicated, you can use low pressure ratios in the compressor and turbine. And that's a great advantage when you're designing compressors. You need intercooling and recuperation to get high efficiency. Okay. Right, well, this is starting to get to the hard part of it. Here we have the compressor. All of this arrangement is running at substantially higher pressure than atmospheric. At the outlet of the pressure compressor, you're talking maybe about 30 bar. But the inlet pressure is maybe about 10 bar. So the whole thing is a pressurized system. Now, as I was explaining about the Rolls-Royce gas turbine, gas turbines need cold air or they don't work properly. So you have a cooler which cools the air coming into the compressor. Comes out and it goes into a fired heater, and that's basically a heat exchanger which is just picking up heat from whatever fuel you're burning. Could be coal, could be heavy oil, could be anything, so long as it's high temperature. The air expands, as I've explained, and it then has got enough energy to drive the turbine that drives the compressor. You've got enough left over to drive what is called a power turbine, driving the alternator. And after that, the hot gas comes out of the turbine and has to be cooled down to a low temperature. Okay. Now, if you think about it, you've got all of that hot gas coming out of the turbine. Why waste it just cooling it? Can't you do something sensible with it? Well, the sensible thing is to put in another heat exchanger, which takes that waste heat and it heats up the air coming out of the compressor before it reaches the high temperature heater. That's obviously more efficient, but click. What a surprising fact of doing all this is that you find that if you want maximum efficiency, the compressor then starts working at a low pressure ratio. And all of that side of it becomes easier to design and becomes more efficient. Okay. So this is what it looks like. Here we've got the cooler again, the pre-cooler. You've got the compressor. In this case, the air that comes out of the compressor picks up heat in the recuperator. Temperature increases to maybe about 400 C before it goes into the fired heater, where it's heated up again to reach a temperature of about 700 degrees. And then it goes through the power turbine, through the turbine driving the compressor, and then it goes into the power turbine driving the alternator, and then back through the recuperator, where it loses a lot of heat and goes to the cooler again. Okay. You can do even more clever things, something called intercooling and reheating. I decided to drop that side of it. But just to say, both of these things, they improve the efficiency and they improve the plant output. Okay. Well, just about the time that Brown Boveri produced their arrangement over at Neuchatel, here is the Escher Whyss plant in Zurich. They built it in their own works. And here it is. You've got turbines, compressors, a fired heater, that's the round thing to the side. And the efficiency is really quite good, 31%, 31.6%. Okay. Now that was in 1939. Now you'd think with technology being what it is, you'd expect, a huge improvement. Well, I'm afraid life wasn't like that. Note the turbine temperature. It's still stuck at round about the 700 degrees. The plant output, well, that was a demonstrator that they had over in their works, producing 2 megawatts. The Oberhausen plant, a very successful plant by all accounts, ran for over 100,000 hours, but it was only producing 14 megawatts. Worked as part of a district heating system. Okay. There was some interest in this country from John Brown, who were talking about a peat-fired system. Here we have everything is shown here. We have the closed cycle heater. We have a combustion air preheater, the heater. And down at the back, we've got the compressors and turbines. And I think they didn't go much further than building this model. They did actually build a peat-fired plant. Go on. And here it is. And you see, it's really quite massive. It's only 1 megawatt output. You're talking about something the size of this room. And that's all it's doing, And that's one of the problems. It's a very complicated plant. Might be efficient, but it is complicated. And it suggests that the capital costs are going to be very high. Well, let's have a look at the turbo machinery. Some of the salient facts. This is, again, a very good German plant at Ravensburg. This was using a centrifugal compressor and an axial flow turbine. But I wonder if you can see the guy bending over these enormous bolts because, as I've explained, the whole thing works at really quite high pressure. It's not going to be a lightweight turbine casing that you need for an aircraft engine. Okay. And it's a similar story over in Japan. Here we've got a unit running on blast furnace gas. Again, temperatures are stuck at 700 degrees centigrade. The efficiency is quite good given the low temperature. But again, have a look at these if you can see it. There's massive bolts. I mean, I think it would be quite amusing to watch these people flogging them up. Go on, right. Well, I have to say, I come here on various occasions. I've come here and I've condemned hydrogen and I've condemned Concorde. Well, what am I doing here talking about the closed cycle? Here we have the powerhouses on the side, but look at this enormous heater. Quite a low output, just over 2 megawatts. Efficiency is not that good. Give it a click. Now this tells you, I think, why the closed cycle was not going to go very, very far. There's the Rolls-Royce Dart turboprop, which is about that sort of size. And this huge plant, admittedly, it's running on coal, powdered coal, which the turboprop obviously couldn't. But you need all of that equipment to produce the same sort of power. Okay. That's the schematic layout of this plant. What I'd like you to focus on is the heater, which is, I'll have to go to the screen here, and the recuperator. You might say two of the weak points of the closed cycle. And just have a look at that recuperator. It's got a very peculiar, why is the artist drawn it in this rather strange way? Okay. Well, here is the heater. You've got this absolute mass of high temperature tubing, something like about 3 inches diameter, to pick up the heat from the burning coal. It's expensive. Okay. And then we go down to the recuperator. Well, if you don't have a good recuperator on a closed cycle plant, you might as well give up. You have to have a very efficient way of picking up the heat from the turbine and putting it back into the compressor flow. And so you need a very sophisticated or a very, very big recuperator. And just let me stop there. When I started the closed cycle gas turbine project in British Gas, it was I only gradually realized that it wasn't just the heater that was going to be the problem. It was the recuperator. And I talked to the guys who were designing the actual heater for me, and they told me that the recuperator was going to be bigger than the heater, and it had to go inside of a pressure vessel. And I thought, God, we're doomed. We're doomed. Okay. Now, in order to keep down the recuperator size, this is what Escher Whyss came up with. I'm sorry, I have to go back to the screen. This is your tube, which separates the backward flow from the flow from the turbine to the fired heater, and you need all of these brazed on fins on each tube to get good heat transfer. And in the right side of the screen, you can see how they're all arranged. You have a block at the middle here to make sure that all of the heat is flowing in the right direction. Okay. And that's what the whole thing starts to look like. Okay, that's inside of the heater. But then you've got, go on. Then you've got to get the fluids into the heater. So you need this complicated arrangement of tubing coming in. And that's why, go on. And that's why the artist drew that schematic of the recuperator in the way that he did. Well, Fred Starr didn't have the money to pay for this, but he's lucky, you know. As they say about people, I don't care whether he's any good, is he lucky? So go on, right. Well, there were probably about 15 to 20 closed cycle units sold by Escher Whyss over the years. And they're all basically much of a muchness, maximum output round about 12 megawatts, turbine inlet temperature 700 to 650 to 700 degrees, pressures round about 30 bar or so, and the efficiency for the size that they had was quite good, 30%. But they were stuck there. Okay. And so by about 1970, that was the end of the closed cycle as we know it. But the Germans realized that this would fit into a new type of reactor that they'd got called the pebble bed reactor. There was some interest in a similar kind of way in this country with the Dragon reactor, but I don't think we got anywhere like as far as the Germans. Go on. 950 outlet temperature. This would produce 45% efficiency. It used helium rather than any other gas, and it used molybdenum turbines. I found all of that very useful when I was selling this idea to my boss. Go on. And here is the interior of the pebble bed reactor. I don't think these are these pebbles are basically a kind of like a mixture of tiny particles of uranium dioxide mixed in graphite and covered with a silica shell. I think this is just basically showing how the reactor gets filled, because I can't see how the people would have stood the radioactivity. Go on. Well, that's basically the hard part of the talk over. And I thought we'd have some fun. A gentleman came along tonight and he showed me the General Electric nuclear-powered bomber. Well, there's a man called Kenneth Gatland in the 1950s. He was very keen on space and very advanced concept. And he produced this idea for flying review of what a nuclear-powered bomber would look like. It's essentially an Avro Vulcan made bigger. Go on. But this, I don't know whether you remember what I kept saying about Concorde being an engineering failure. It didn't have the range. Well, this closed cycle gas turbine, Concorde, would have had infinite range. You have a central reactor, and that is pushing hot gas round to the engines, which produce your jet thrust. I think we should have gone with this rather than the silly Concorde. This is a much better idea, you know. Of course, it would never crash, unlike the other Concorde. Go on. Well, here it is. And again, I'll have to go back to the screen, I think. I do apologize. I hope people can hear me. You have your reactor running at quite a high temperature, say 1,000, 1,100 degrees centigrade. That's taking helium from the compressor, going through the reactor, heats up the helium, and there's enough power then to drive the turbine, which drives the compressor that circulates the helium around the circuit. But there's also enough power to drive a compressor which is taking air in from the atmosphere. And that compressor takes air around to a heat exchanger, which is taking the hot gas from the turbine. There's no turbine at this back end. This is just producing a very high velocity airstream. I think it's a wonderful idea. And I think we should get the next Labour government to invest in it. Okay. Right. Now, you've heard about the closed cycle gas turbine shortcomings. The heater needs high temperature alloys, unless you're using nuclear heat. The recuperator, as I say, is a complete nightmare. It's bad enough that in terms of heat exchanger terms, it's a nightmare, but it has to go inside of an insulated pressure vessel. And then you've got sealing and lubrication issues, particularly if you're running a nuclear cycle and you've got helium. You don't want oil to get into the helium, and you don't want the helium to leak. And you need specialized industrial know-how. The only people who knew anything about it really were the Swiss, particularly Escher Whyss. So, click. So I had sold this idea to my boss, and he told me to go and get something built. So I started trekking around the country and asking gas turbine people this question: can you sell us a cheap, I haven't got the word cheap in here, a cheap high temperature gas turbine with an inlet pressure of 20 bar and an outlet pressure of 7 bar. Click. And that is the reaction I get. And I tell you that as soon as I started telling people what the turbine inlet temperature was, they'd start telling me I'd got things completely wrong because they had no idea about designing systems which had got intercoolers, reheat, and recuperators in them. I had to tell, it was embarrassing to tell people who were supposed to know this kind of thing some basic thermodynamic facts. Go on, right. So now we move on to the work I did in British Gas. Well, the problem with the ordinary closed cycle is that the heater is damaged by the ash in the coal, and you're limited to heater temperatures of 700 C. But natural gas doesn't have any ash in it. It's very clean. And out of the gasification work I'd been doing, I'd come across a really new material which defied or appeared to defy all the normal laws of high temperature materials, because it relied on having very, very tiny particles of yttria to keep it strong inside. And unlike normal high temperature alloys, these things didn't dissolve in the material when the temperature went up. And so it looked like we could run with heater temperatures of 1100 C. Okay, right. And I was told, well, you know, walk the, what is it? Don't talk, walk, you know, get on and do it. And so I started on it. Okay. I'm not going to go into the complicated ways that we had to build this thing, because we had to, like engineers have to do, you have to make compromises. And this whole arrangement is a cycle, is an arrangement, so we could use the equipment that we've got. Okay. The first thing was to get hold of a turbine. And I went around a lot of places, and I ended up at Westland Aircraft, because I thought they'll be using small gas turbines. And the chap there was very kind. He actually understood what I wanted. And he said, look, you don't need a gas turbine, an expensive gas turbine. Go and talk to Helseth Limited, who make turbochargers up in Huddersfield, which I did. And this is what we have. Okay. Oh, I should go back there.
Yeah.
Another problem was, well, where would we get a generator, you know, running at, say, about 100 kilowatts, turning over at something like about 60,000 RPM? There isn't one. So the way I got over that was to get the gas turbine, sorry, the one turbocharger to drive the compressor, but also with the spare energy that drove a turbocharger, which then drove a compressor to absorb the power. That was my way of getting over that. Okay. Here is the high temperature heater. It's made by a company called Metallurgical Engineers. The specialized alloy came from Belgium. We couldn't get Henry Wiggins to stay in the project. Okay. And here it is getting built. You need very, very small diameter tubing. We found out almost by accident that we couldn't weld the material. We had to explosively weld it into a high temperature alloy and then join that to this header here. Okay. That's what the heater went inside. Okay. Here it is inside. The tubes are on the left. And here is my salvation. Here is the recuperator. I explained, that I was told that we would need a recuperator as big as that furnace I was showing you. And I was told about something that British Gas were thinking about using. I got the people to come round, and I said, this is exactly what we need. This is a heat exchanger, which is very effective. It doesn't need a pressure vessel. Go on to the next picture. And this is how it is. This is the outside. The bottom thick piece is effectively the pressure vessel. All of these other plates are being made by printed circuit technology, etching the heat transfer passages into the plates and then putting them into an enclosure and sticking them together by diffusion welding. And that got me out of trouble, Okay. So you saw the picture at the start. This is what it looks like. We've got the heater furnace on one side. All of the rotating equipment is unfortunately round the back. We have the cooler. Okay. Now, I told you at the start of this, we're getting right near the end. I told you that if there's one thing that this project did, it made a lot of people in the high temperature corrosion field very happy, because if there's one thing that they want, they don't want materials that work. They want materials that corrode. And I was assured when I went along to Henry Wiggins and to the people over in Belgium, oh, you've got a material here which is impervious to high temperature material, to corrosion. Well, you see, this is where my age came in useful. I knew what had happened in the atomic energy in the nuclear side. They had been told that carbon steels would last forever in carbon dioxide. And then after about 5 or 6 years, they found that the carbon steel started corroding very, very rapidly. And I insisted on long-term tests on this material. And I well remember taking the tube in which we've been doing the testing across to a conference in Belgium and showing the people there that, yes, it was absolutely wonderful, not a sign of anything at all. A nice grey impervious aluminium oxide. We then brought it back to Britain, restarted the tests, and then we had a failure of the furnace about 600 hours later. And when we opened it up, we found these huge black incrustations where the alumina layer, which had been protecting the steel, had disintegrated. And what is happening there is just simply the steel itself is starting to corrode. And steel doesn't like air at 1100 C. But because of this, a lot of people started doing PhDs and the like to find out if they could improve this material. Well, they haven't. But it's made a lot of people very happy. The other problem with the alloy, which we did know about, we started to know about once we got talking to the alloy producers is that the material is very, very strong, but it's strong in the wrong direction. It's a bit like a piece of wood. If you try and pull a piece of wood apart, you've got the grains in the right direction. But if you try and split the grains, it just breaks in two. And you've got exactly the same problem with this material. It turned out to be a lot weaker than we expected. It was better than other materials, but nothing like what we wanted. Okay. Well, the only hope for the closed cycle is things like the lead fast-cooled reactor, where you can use helium to extract the heat. And okay, next one. And the molten salt reactor. And again, the closed cycle has got a place there. Okay. Well, it had a good run for its money. I got a lot of fun out of working on it. I learned a lot, which helped me in subsequent jobs. It's easy to estimate the power and the efficiency, but it's best in niche applications. It could have an option in district heating, waste incineration, I think. But you've got the problem with high temperature corrosion, and with both steam plant and conventional gas turbines, they started to leave it behind in terms of an efficiency. And the people who really know anything about it are no longer with us. Thank you very much.
Right. Bear with me while I just end the share. Brilliant. Okay. We've still got lots of people online. Good. Any questions in the room first, to give a chance for people online to put their hand up or write a chat?
What was the version of the Bristol thesis turbine turboprop with a heat exchanger? Was that heat exchanger really meant to be a recuperator?
Yes, that's right. And they had the same problem. The problem with recuperators on a normal gas turbine is everything is quite lightweight. And the other feature of them is that the startup and shutdown times are very, very quick. In the closed cycle, you've got a huge mass of material in, so that because everything cools down at a relatively low rate, you don't get high thermal stresses. And that's been the problem with the recuperator. People keep coming back to it. And you could theoretically, I think, produce an open cycle gas turbine, certainly for land-based, but it would have to be handled with kid gloves. The people would have to know what it was. For aircraft, I think it's out. All you'd need is 1 or 2 crash shutdowns at altitude, and here you recuperate running at, say, 600 or 700 degrees, and then it gets a blast of cold air. And there's another problem too with recuperators on a modern gas turbine. You take a lot of air from the compressor to keep the turbine blades cool. And by doing that, you're unbalancing the flows over the recuperator, you have a lot more air coming back from the turbine than coming from the compressor, because a lot of that air from the compressor has gone through to cool the turbine. But the Theseus was an early attempt to do this.
There's a modern gas turbine. There's a modern gas turbine. With a heat exchanger in the exhaust, and it's being used by the Navy in the Type 45 destroyers, the WR-21. Yes.
Well, I remember boasting about that in 2000 and saying what a tremendous thing this would be for gas turbine plants that needed to start up and shut down quickly, because I think I was one of the first people to bang the table really and say, look, you've got a problem with power plants having to shut down and change output because of the day to night variation in load. And I said, just you wait until you get wind power coming along, because you can't guarantee when the wind is blowing, and you'll be having to shut down your equipment very, very quickly. And I said that the WR-21 was looked a good way, but as far as I understand, it's had a lot of problems for the same sort of thing that I just talked about. Your recuperator is having to go through a lot of thermal cycling.
I understand.
And I'm quite embarrassed when I look back at this paper from now 25 years ago, in which I was the plenary speaker at this Parsons conference, talking about plant cycling and the future and what possible options we've had.
Okay, I've got a message. Let me just get one here for a moment. I've got a couple come through from Gordon Taylor online. One of the question there says about the suitability of the combined cycle gas turbine for pure hydrogen fuel. And then the other one is regarding any once through nuclear cycle, I suggest you look at the availability of uranium fuel. Present consumption is 70,000 tons per year, and it is fast depleting with long time to open new mines with even leaner ores. So two questions there. Firstly, hydrogen.
Well, my answer to hydrogen is what I say about Mrs. Beaton said about making a hair pie. First catch your hair. And as I've said, I say repeatedly, and there's a letter from me to the Institute of Materials. I can't say long and loud enough that the cost of hydrogen is 3 times the cost of the electricity from which it is made. It really has, it is a niche, certainly for power generation, it's a niche area. And certainly for nuclear power, I used to worship it. I really know I'm very cynical about nuclear. So I put nuclear up just to show what might be. But it's quite surprising that those 2 plants that I showed, the 2 options that I showed, the lead-cooled reactor and the molten salt reactor, the operating temperatures there are only about 700 C, because if you're putting metals in contact with molten salt and you're putting or molten lead, they're going to react. So you have to keep the temperature down. And that's why you're stuck at 700 C. The pebble bed reactor, in principle, is better. You don't have any tubes in the reactor. You just got hot helium going through the pebble bed. But the plant over at Jülich turned out to be a nightmare, and nobody knows how to shut it down. They filled it up with concrete, and they don't know what to do next. With that,
Well, can you hear me?
Yes, Gordon.
Oh, fine. I just wanted to underline if the availability of fuel. It's after all, uranium is in effect a fossil fuel. Okay, it may not contain carbon, but it's a mineral resource, finite, and therefore it's like the peak oil business, guys. We're past peak uranium. Once it's gone, right? So I suggest anybody who's proposing such schemes, whether they're big nuclear plants or little nuclear plants, as anybody who knows any thermodynamics will tell you, are less efficient. Therefore, they're even more wasteful than big nuclear plants. And that's, we also know they're on Putin's target list, don't we? Hostages to fortune. This is lunacy. Anyhow.
I would agree with you.
Thanks, Gordon.
Yeah. On the hydrogen thing, I just put up a sentence. I've actually arranged a talk about hydrogen bioelectrolysis by this fellow, Henrik Stiesdal. He's got a website, it's stiesdal.com. And he's giving us a talk on May the 1st from Denmark. And if you look at this other website, Chelmsford Science and Engineering Society.org.uk, for May the 1st, you can log in on it.
For those who can't see that, the website that Gordon's put up is just cses.org.uk.
That's it, yes.
Thank you, Gordon. There was a question at the back, sir.
Good.
Talked about nuclear power plants, but that nuclear bomber, would it not have required some cooling arrangements on the ground?
Okay, the question was about the nuclear bomber. Would it have required some cooling arrangement, did you say, or fueling?
Correct.
Cooling, some sort of cooling arrangement on the ground.
That's a good point, but I guess you'd have to run the thing you'd have to run it for a couple of days to get it quite cool. But of course, you'd put the control rods into the reactor and bring it down to reduce it to a low temperature. So I don't think it's insuperable, but it's a good point you make. I'm just starting to think now about once you got the thing into the air, you'd have to say to the passengers, well, we're going to go around the world 3 times before we can land.
There was a question, Brian, you had a question.
Yes, I did. You mentioned helium, which I assume that because it has a better ratio of specific heats, it's more efficient. I was wondering if you considered using that in your plants with this gas.
Okay, the question was about helium in terms of its better
No.
heat. Was that considered it being used in your plant?
No, you couldn't use it the problem is with helium, it's got a very low density, and you cannot get the pressure ratios unless you use a very, very large compressor. You just get a small pressure ratio at each stage. Well, we were using helium, but it's a good question, Brian, and I kick myself because it took me a long time to realize this. I should have used argon in this cycle rather than helium. It had got a better density. Its ratio of the specific heats was better than nitrogen. We would have got better temperature ratios, which would have helped us with the design of the thing. But I only worked that out 20 years after the plant had been scrapped. But the reason why helium is used in nuclear reactors is because it doesn't absorb any neutrons. It doesn't become radioactive. Almost any other gas you put through will pick up radioactivity. So it's, yeah. Yes, yeah. Helium is your only option in nuclear reactors.
There's a question here about comparing the closed cycle with the alum cycle.
I knew I should have done that before I came here. I don't know, really, I don't know enough about that. Maybe the gentleman there could say something about the alum cycle.
You're on mute, Gordon.
Likewise, Fred, I can't really tell you in short form. I just know of its existence. So it's, but I do know that it's based in US and it is receiving funding. And it certainly does involve some kind of closed cycle and some kind of pressurized circuit.
Maybe a theme for another talk in the future, perhaps.
Yeah.
Any questions from the floor? We exhausted the question. One more from Brian again.
I can't remember what sort of efficiency you got out of the plant that you built, Fred.
What efficiency?
Did you mention?
What efficiency did you get from your plant?
I don't know. I have to say this. What happened is that I was asked, basically told to switch divisions, and I could either stay with the closed cycle or work on Stirling engines. So although I'd got all of the bits together and I'd brought all of the players together, and I sorted out quite a number of technical hitches, for various political reasons, I was pushed out. So I don't know. I would think it probably would be about 5%, something like that. I'd be surprised if it was higher than that. One of the things which I explained about that complicated diagram, a principal aim was to prove that the heat exchanger would produce nitrogen, pressurized nitrogen at 1100 degrees centigrade. But we knew that the turbocharger couldn't take that kind of temperature. So there was a secondary system coming off the compressor, bypassing the heater, that brought that temperature down to something like about 800 C. So it couldn't possibly have been very efficient. The turbocharger itself was not terribly efficient. I mean, truck type turbochargers are good, but they're not good. The compressors are very good, but the turbine part of it, it's a radial inflow turbine that was being used, is not terribly efficient. It doesn't have to be.
I did notice on one of your slides, Fred, that you mentioned a figure of 52% overall efficiency, which was really quite good when you were thinking of the period that you were operating. But it's not difficult to understand why the combined cycle gas turbine has held sway since your days of experimental work, because you're now talking about in the 60% overall efficiency.
Yeah. I mean,
It was a very interesting period that I hadn't really appreciated just technical problems that you had, far more complex than the combined cycle gas turbine, which I was fortunate enough to be involved with at the project level in those early days in the 1970s.
well, the combined cycle gas turbine didn't really start getting off the ground until before they started introducing air-cooled turbine blades, and that would have been round about something like about 1990. And I remember going to see the first combined cycle plant in this country, up in the northwest, near Barrow and Furness, and that was running at 47%. And I used to go along to IMECE conferences and watch with horror as the combined cycle efficiencies were going up and up and up. And I think I would have ended up with a tremendous row with my boss, because he kept saying, oh, they'll come up with better materials. Well, I was a metallurgist. I knew what we had was the very best we could get. We weren't going to get more than about 51, 52%. Even with everything on our side.
Okay, any more questions in the room? No, I think we're done.